Hello, everybody. I'm Peter Trentafilou, and today I will be talking to you about DBEst++, which is a new learned approximate query processing engine that we've developed. So let me start by giving you our take on integrating machine learning with data management overall. As you know, this is an active and fertile field where ML models are being used to develop a lot of essential functionality provided with the traditional data management systems. But what we think is missing is to consider what will happen when all of the systems indeed start replacing boxes within the data management system, and what will be the total demand on the resources which are scarce, such as memory. So what we're actually trying to do is we're trying to revisit what we call the universal model approach. The universal model approach constitutes what now is regarded as the best practice in the community, where a single model is developed that can be used to answer all possible queries given a particular schema. And this model could be, a sample of the data, or it could just be a machine learning model trained on the data, on a sample of the data. So this is fun and it makes a lot of sense. But if you start again thinking what's going on with respect to the global picture, we're trying to push towards adopting what we call a model per query template approach, where we develop a lot of very tiny, lightweight models. And the question we ask is, why keep massive model that can be used to answer all queries, making very stringent demands on memory, when we know beforehand that only a small fraction on all the possible queries will be asked against that schema. So we're pushing towards maintaining a multitude of such light models which can reside in memory. And we can maintain thousands of them in memory, and if not, for a fraction of the cost, and if not, we can simply just go and fetch them from SSD and deserialize them, a process that will take only a few tenths of milliseconds. Or even if we're operating in a distributed environment, we can just go to a remote data node and fetch the model and deserialize it, paying negligible bandwidth costs. So we will show in particular that these such light per query template models can not only provide the obvious huge benefits in terms of memory requirements and memory footprint, but it can also achieve higher accuracy and faster query processing time within the context of approximate query processing engines. So the overall vision that we're heading towards is a vision where we manage models and data, and we will be talking about learned data management systems in future, where basically we will forget all about data and we will simply be playing with models for the vast majority of the provided functionality. So let us start describing now what is this new engine all about. The first thing to note is that it's based on the DBEst AQP engine that we developed a couple of years ago, and it was published in Sigma 19. These are the typical queries that it supports, where you have a bunch of grouping attributes, aggregation attributes, attributes that are continuous or ordinal, where you can specify range predicates on them, or attributes that are categorical, and you can basically have equality or non-equality predicates on them. And DBEst was based on using regression models and kernel density estimators, and the simple math and the simplicity of the approach was perhaps its biggest advantage, was that you can basically, if you have density estimators and regression models, you can combine them like so in order to come up with answers to the particular aggregate functions. So we saw an example of 3 aggregate functions here. So what our quest for improving performance basically was stemmed from our desire to improve performance by reducing further the relative errors, by reducing further response times, and also by facilitating updatability of the models as new data will be coming in, as in a real-world situation, instead of having to retrain the kernel density estimators and the regression models as DBEst does. So to do this, we used mixture density networks that can deliver on all of these fronts. And essentially, MDNs compute, given an input X, they compute the probability of particular values for Y. And they do that by basically providing a mixtures of M Gaussians, where M is a hyperparameter. Basically, they work like so, given an input X. There is a bunch of hidden layers, and in the end, the output layer delivers for every Gaussian out of the M Gaussians a mean value, a standard deviation, and the weight of that Gaussian that can be used in order to come up with the overall mixture. So In addition to using MDNs, mixed density networks, we use word embeddings, and by the basic reason for this is that our insight was that we can further improve on accuracy by considering attribute values as words and tuples as sentences being comprised of the values of the attributes that make up the tuple. So basically, we use word embeddings, where words here are the values of particular attributes and sentences are the tuples. And the location of a value of a categorical attribute in an embedded space will depend on the context. In this case, the context is the surrounding values of the other attributes. So putting it all together for the queries we're talking about, so we basically train the MDN. We maintain an MDN for density estimation by providing as input the word embeddings for each of the key attributes. And basically, using this density, we will be able to provide this MDN density will be able to provide the values for X, the probabilities for the values for X, given the grouping, the attribute values, and the values for the other categorical attribute in this particular example. And for the regression, again, with the same query, we will be able to train an MDN model, which will be able to provide basically the value of the aggregation function, a regression model for the aggregation function, given the previous values of the attributes that are engaged in the particular query. And during inference time, we will basically be using the MDN for the density in order to come up with the density of X, where X is the continuous variable here, and the MDN for the regression, and we will be able to come up with the values of the aggregation, or for a model for estimating the values of the aggregation attribute Y. And the output would be an estimated value for Y per given group. So we conducted a large number of experiments. I will not have time to go through all of them. Please look at the paper. So we looked at the queries that, like the ones that I explained earlier, and we compared against the state-of-the-art sampling-based approach, which is VerdictDB, and the state-of-the-art learned approaches, which is for approximate query processing, which is DeepDB and actually DBEst. And for DeepDB, we will consider two different versions to be fair. One we call DeepDB Universal, and another one which we call DeepDB Compact. And let me dive quickly into the results. With respect to relative error, you can see that DBEst outperforms both VerdictDB and DeepDB in particular for sum and count, but for overall as well, by about an improvement of about 40% in relative error. And here we basically use different scaling factors for the TP-CDS data set and the queries that we have on that. And again, we see the same results with respect to the relative error. Performance is improved by about 40–50%. And also, so what we did is we looked at query processing times and space overheads, and again, query processing time is about 50% better, whereas space overhead is an improvement of several orders of magnitude, more than 3 orders of magnitude in this case. So we also want to compare against what we call the compact version of DeepDB. This is basically DeepDB being trained with only the attributes that are involved in this particular query template. And again, we see that DBEst outshines the compact version of DeepDB. And notice also that the compact version of DeepDB outperforms the universal version of DeepDB, which is very promising indeed for our approach. So the memory footprint here, we see again up to 120 times improvement compared to compact DeepDB. And similarly, here with a flat data set with 1 billion rows, we see a big improvement in space overhead as expected. So to conclude, we have presented the DBEst++, which achieves state-of-the-art performance in terms of memory, response times, and relative error, and puts forth a new perspective towards maintaining a multitude of lightweight machine learning models versus universal models. So with that, I would wish to end, and again, thank you for joining us. Bye-bye.